Workplace Planner, the focus is to link an Excel spreadsheet of work tasks that people perform with a layout drawing where they perform the work. So we're essentially linking an operator's work process, their circle of work. They do a task at a location, they walk somewhere. They do a task at a location, they walk somewhere. And they may do this over and over and over in many cycles with a scaled layout drawing where the work is performed, so that as we modify the layout, we can see the impact of walking on that person's cycle time, on their process flow. And by using the diagrams that Workplace Planner generates about how the operators walk through the facility, it really helps us understand how we can improve the layout to reduce the walking component. It probably goes without saying that Workplace Planner is very layout centric in its analysis. In other words, if you were just going to do a process analysis where an operator stands at a location and never walks, Workplace Planner probably isn't the solution for you. Workplace Planner is best applied to situations where the operator does do quite a bit of walking in their overall work cycle. So in the drawing that we're looking at here, this is a classic output of Workplace Planner. We have an AutoCAD layout drawing and we have text labels where work is performed. We load a spreadsheet of process tasks that are in sequence and have a time specified. And as the operator goes from task to task to task, where some of those tasks may require the operator to perform them at a different location, the program will automatically draw a line to that next location, show an arrow in the direction of flow, show the distance of the walking, calculate that into a time, and add that to the operator's overall cycle time. So as a result, we end up with an analysis that may look something like this. Here I actually have an operator and I have a hoist where the operator uses the hoist, so I can have multiple operators, one or multiple operators, and I can also have one or multiple pieces of equipment. And that equipment can be stationary or it can be dynamic. Now you may ask, why would the equipment, if it's stationary, or even to some extent if it's dynamic, in other words, that it moves, be relevant for Workplace Planner analysis? And that is because operators and equipment can interact in such a way that they block one another. That means that an operator may have to wait for a piece of equipment to be available or wait for another operator to be available if those two operators need to do a task synchronously or essentially at the same time. So that creates what's called an internal delay. So what we're going to be looking at here is we can see this operator here. We see that there's a walk distance for their total cycle. We have a total cycle time. What percent of time are they walking? What percent of the time are they doing value-added work? What percent of the time are they doing non-value-added but necessary work? What percent of the time are they doing non-value-added work? Okay, and this is a round off error on the -1 here. And then what percent of the time do they have an internal delay and what percent of the time do they have an external delay? That's what ID and XD mean. So internal delay would mean that the operator is actually waiting on a resource. So you can see in this case, the operator waits on the hoist becoming available 4% of the time. The hoist in this case waits on the operator 88% of the time. Obviously, we don't really care about how much time the hoist is waiting, unless of course the hoist is a critical resource. And we have a classic man-machine problem where we may have multiple people working to keep that machine busy. External delay would be a situation where the operator cannot begin work or the operator may end work early and have to wait until their next cycle comes up. So before they could start work again. So external delay is time before they start or after they end, before their cycle can repeat. That would typically be a case where I have multiple operators and one of them has to wait for the other one to finish before they can do the cycle. So that's essentially what Workplace Planner is calculating. This is an example of a Workplace Planner input file. One of the things you'll see how Workplace Planner is designed is it's targeted to really sit between AutoCAD and Excel. So I have an Excel spreadsheet of routings, and that could be authored directly in Excel. You can do some authoring in Workplace Planner, but the interface really isn't ideal for that. And this file could also be generated externally by another application. What we're looking at is we have multiple, operator tasks or steps. All right, my mouse is messing up here. And we see operator one, operator one, operator one, walk, process, M is a processing task, W is a walk task, it's a manual walk task, or manual processing task, sorry. W is a walk task, M is a manual process task. Now, we could specify in column D an actual time, or we can put in a predetermined language, such as MODAPS in this case. And one thing that's interesting about a predetermined language is that while the processing task, the manual processing tasks, code M in column B, may reference MODAPS codes, they're used to compute an actual time. And we actually see a time in column K. So the software parsed the MODAPS codes and generated the time for that task. That's just classic predetermined time parsing. However, in the case of column D, whatever the, for walking tasks, whatever the operator enters, in this case W12, is really irrelevant. Why do I say that? Because the software will compute the walk distance from the drawing, figure out what the proper MODAPS code would be to walk that distance, and then it automatically updates or replaces whatever was in column D with the appropriate MODAPS code, and then of course computes the actual walk time shown in column K. So J, K, and L here off on the right are good examples, or J and K in particular. Actually, L is a value-added, non-value-added definition. But J and K are computed by the application, the time that's computed and the distance that's computed. And in some cases, the distance is computed time. It comes from a computed distance from the drawing. Column L represents whether the task is value added or not. Now, by definition, walking is non-value added. So the software is automatically going to populate column L's walk rows with a 0. However, the operator can put in the value or non-value added but necessary. In this particular case, you can see row 3 is a MODAPS code to obtain a hub. Now we're going to assume that that's a non-value added but necessary task. So we enter a /100. If it was a value added task, it would be 100. So you're starting to get, hopefully, that handle that it's the value / non-value. So as I come down here to row 16, you can see obtain overhead multi and bring down something 50% value added / 50% non-value added but necessary. Now remember, the / is non-value added but necessary, or non-value added required. What that means is you don't specify non-value at all directly. It's always the remainder. So if we look at row 5, I have 50% in there. There is no /, so there is no non-value added but necessary value. The software will always take the remainder of the value and non-value added but necessary and make that non-value. Okay, so first row is 100% non-value. Second row is 0% non-value and 0% value. It's 100% non-value added but necessary. Row 3, 100% non-value. Row 4, 50% value added, and then the remainder is 50% non-value. The next row, of course, 100% non-value added but necessary. The next 2 rows are 100% non-value. You get the idea, hopefully. You can see we do have some rows here: place onto dust shield, aligning hole, ABS units, feed ABS wire through dust shield. Those 200s represent the fact that those tasks are 100% value added. So it's really not super complicated to define this list of tasks. You can see they're all listed for the operator. We can also see that as we go down towards the bottom of this list, rows 30 and 31 and 32, and I apologize for those being right there at the bottom, but hopefully you can see them okay. We have another interesting situation. You'll see me do this in a moment. Row 31, operator 1 and the hoist are going to both need to be available before the next line of this process list will be evaluated. What do I mean by that? I basically mean that all these operator tasks have to be performed and this one hoist task has to be performed before the operator and the hoist are both available. Now, they will occur concurrently. In other words, each operator works in parallel. So the operator and the hoist both start out. Initially, the operator 1 is walking, doing a W12, and the hoist is also being moved W12. Now you can see at this point, the hoist is available, but the operator is still busy. So the hoist is going to wait on the operator until the operator does all these tasks until row 31. Once all the rows have been processed prior to row 31, then the software will process row 32 and beyond. In other words, at that point, it goes parallel again. Operator 1 does their thing, the hoist does its thing. But obviously, there's an internal delay. Now, by looking at this spreadsheet, it's pretty obvious that once they start off and both do their walk 12 motion, the hoist has no other tasks prior to this synchronization on row 31. So the operator, the hoist is going to wait for this whole time until the operator is available. And as I go back to the summary, you can see the hoist waiting on the operator. Totally makes sense. Okay, so the other thing the software is doing then is, since I did classify time for the tasks, and I am identifying time spent walking, and I am identifying situations where one resource or operator has to wait on another, we end up with a situation, and I'm also classifying when tasks are performed, whether they're value added or non-value added, but necessary or non-value added, or whether they're internal delay or whether they're external delay. You can see pretty clearly why I can generate this bar chart, or these set of bar charts, one for each resource, because I'm actually able to show what percent of the cycle time is spent by each resource, operators and machines, in these various areas. The other thing I can do is generate a report. And when we generate the report, we're actually using our process symbology, our operate, our transport, our delay, our inspect, right? So our store. Those are the classic industrial engineering process symbols, right? So delay would be internal, external delay. Inspect is another thing I can specify when I'm processing, whether I'm inspecting or not. I'll show you where that gets entered. And then also whether I'm in storage or essentially being held up in a bin waiting to be processed. So this allows me to take these different steps, identify the process symbology, where they're performed, and this is just a user-defined location. It's essentially going to be represented in the Autocad drawing as a text label on a certain layer of Autocad. So table-hub will be an Autocad text object in the Autocad drawing on a certain layer. Table-fixed will be an Autocad text object. Mid.wc will be an Autocad text object located somewhere in the drawing. The software, Workplace Planner, will look at where it is and automatically draw walk lines to and from those location spots in the drawing and calculate their distances. And that's how distance and time is computed off on the right, hence our summary report. Now, this is a great example of how Workplace Planner is used for what we call static workplace analysis, which means that while the operator and the tools are moving, when the operator is performing the work is stationary. We're going to take a quick overview look at a moving product study, essentially. What that means is that while the operator is working on the product, the operator is also moving. Okay, this is a very unique situation typically used in the automotive industry, where on a moving assembly line, the operators, when they start a task on the vehicle, they may stand on a flat top conveyor and move with the product, which means that when they leave the vehicle, they're not in the same spot they were in when they got to the vehicle. Now, this is pretty important in a walk path study, right? That's often referred to as a scrolling analysis, is that when I'm calculating operator walk distances, I need to know where the operator is at every point in the cycle time. So this is a little more complicated. The software Workplace Planner was designed to handle it, and we'll see how it works in doing this. But this is a great example of a drawing showing you the operator walking from different bins and storage areas for parts in the workplace to the vehicle, and then leaving the vehicle and going and getting other parts, and then going back to the vehicle, and so on. Of course, as before, we have an operator on the right, we have an operator on the left, we have a cycle time, We have a walk time, we have a value-added and non-value-added analysis. Okay, so let's go ahead and get out of PowerPoint here, and let's just take a look at how this works. And I have a simple little example. This is actually a university example, but some of you may have, that are watching this may be familiar with this from your class. It's just an operator that will do a static analysis doing these tasks. So the operator walks to this raw material location, takes 3 seconds, does some processing on a saw, and then they may walk somewhere else to L1, and then they process for 10 seconds, then they walk to L2, and so on and so on. So actually from the raw materials area, they're walking to the saw, and then they're walking to L1, and they're walking, right? And then they have their finished task here. When we take the manual time and the walk time and the machine time, we end up with a total cycle time as shown here. And this is the walk path that you see. Okay, so let's take a look at what that would look like. If I go into Workplace Planner, and I just happen to have this loaded here, I'm going to actually calculate this in just a moment. But you can see I have this operator. I actually am doing a process and walk to. So in this case, it's another view. Instead of using M and W, where I have process on one line and walk on another line, I have the opportunity to do what's called walk to and process at. So what I'm basically doing is, in this case, I'm walking to raw, and then here I'm going to saw, and I'm walking and processing. So I have a 15-second processing time, a 13-second walk time, and then I go 10-second processing time, W15, it's not 13 seconds, sorry, it's a W13, W15, we can actually look at what that total time is, 16.68. So at 15 seconds for the processing time, obviously the walk time is 1.68 seconds. And so this is another way to combine the two. It's an option that you have for specifying time. Once again, you're only specifying the fixed time on the left. The software will automatically, since I'm in a MODAPS analysis, put in the time on the right. If I want to do this as a MODAP study, I don't have to do this as a MODAP study. I can actually turn the MODAPS analysis off. In this case, I have a process parser none. And if so, then we'll do a calculation and see what that looks like. So the next thing I've done is I've gone into AutoCAD and I specified these locations. Now I've already done this. So let me just go ahead and delete. I'm going to delete L2 here from the drawing. Okay, just to show you what happens if you're going into a new drawing of AutoCAD. The only thing that's important with your AutoCAD drawing is that it's drawn to scale. And so let me just talk a little bit about AutoCAD. So if I go into the units command in AutoCAD, and just so that we're really clear here, I'm going to go ahead and type in units. Okay, sorry, units. And I can see that I'm in architectural units. In this case, I actually want to be in engineering units. I strongly recommend that for the American organizations where the layout drawings are typically feet and inches. If you are a international organization, non-American based group, chances are pretty good you're going to want to stay into decimal, okay? Those are your two choices. I probably wouldn't recommend architectural. And of course, if I'm in decibel, I'll probably use millimeters as my base unit. If I'm in engineering, I want inches to be my base unit, okay? The other thing I'm going to want to do is then make sure that when my drawing is drawn, that things are to scale. So that if I do a distance, I'm just going to do a rough distance from here to here. You can see that's about 3.5 feet. That's about right for the size of this rack. So my distances are correct. So now that I have an AutoCAD drawing drawn to scale, my units are specified correctly. The next thing I'm going to want to do is make sure in my settings that the software is also seeing that I'm in the proper units. You need to make sure that Workplace Planner's units matches the drawing. Now, if this drawing was drawn engineering or architectural, Workplace Planner should be able to figure it out pretty quickly what's going on. And it did. Output units are feet, input base drawing units are inches, we're in good shape. If the drawing units in AutoCAD are decimal, then it really doesn't know what the base unit is. Is it a millimeter, is it a meter, or is it even inches? And so make sure that it'll probably default to meters on the output and millimeters on the input if your AutoCAD drawing is in decimal units. So just be careful of your units. Okay, the next thing we're going to do is we're going to do a calculation. We file open. I've grabbed that spreadsheet file that we're looking at right here. And in this case, I'm not going to do a mode up study. I'm just going to use those as times. That's fine. Those will go, those W's will go away here in just a moment. I'm a stationary analysis, which means the product is not moving. That'll be the default. And I just do, literally just do a calculation. It says some locations are missing. Would you like to add them? Sure. It wants to know where I want L2 to be. I'll put L2 right over here. The software added L2. So notice there are some polylines in the drawing. I'm going to go ahead and delete those. And there's my L2. You can see the software updated, and there's my walk path for the operator. The software has gone ahead and entered the distances for each of those, and these are all controllable. I can go in, you can see I have a number of tabs here in Workplace Planner. I can go into the paths and I can change my arrow sizes. I can even get rid of arrows. If I don't want arrows, I get rid of arrows and calculate. You can see they go away. I can go to paths and I can add my arrows back. I can change the dimensions of the arrows as I wish to. I can also add path labels. I can delete the path labels. I can update, add the path labels, however I want to make the labels any size I want. All pretty easy stuff. The other thing I can do in the drawing is specify information about the operators. By default, I've got an operator working at 4.17 feet per second unloaded, loaded 3.33. I can change any of that. This editor is a little simplified. So if I do change something like change that to 5 feet per second, I just make sure I need to hit the update, and you can see it updated right up in here, and that'll get shown up in the drawing. The other thing I can do is specify what AutoCAD block I want to use. There's a number of blocks in this drawing for the car or the machine or whatever this resource is. Typically, I look at it as an operator that I want to use. And I happen to have a symbol that's included with the Workplace Planner called PP_person that you can use for your symbol of your operator. And I'll show you why that might be important here in just a moment. If you ever need to go to AutoCAD to do something, you just click go to AutoCAD, you click in the drawing to activate your mouse. You can see I can then window around here as I wish to, and then come back and return to the Workplace Planner interface. So I can jump back and forth pretty easily. I can also change where I want the operator to start at, what color I want to use for the operator's walk path. In this case, I'm using yellow. So there's a lot of different values that I can specify. So the locations, by the way, as you notice, the software prompted me for the location. It read the locations from the drawing. These location text labels are stored on a certain layer, and that particular layer that they're stored on is specified in this particular area of the software. You can see that location text layer is PP_locations, which is the default, but you can change that and use a different one if you wish. The path layers are automatically created by the software, and each operator has its own path layer. Okay, as I mentioned, I did a calculation. The software generated this walk path line. It calculated those walk distances. It updated the distances you see here. It updated the processing times you see off on the right. And just calculate that one more time just so you can see how that works. And you can see over here that the total cycle time for the operator is 160 seconds. The distance traveling 66 feet. They're doing 23% walking. They're doing 77% non-value added time. That's because the lean percents on these are all 0 right at the moment. But if I said this processing time is actually value added, I could put 100 on there and update that row. If I said, and you can see I have different symbols. So I could say, well, that actually is an operation time. So I'm actually processing that and update that, okay? I could say, you know what, this particular task is an inspection task. And I'm going to say that I'm going to consider that to be /100, 100% non-value added, but necessary. I may choose to do that. This one, I could go ahead and make an operation task. I could say that that's 100% value added, and so on and so on. And then when I calculate that, you can see that the software is going ahead and updating these values here. Since I don't have two operators, I don't have any interdependency between them. There's no internal delay. There's no external delay. When I look at the lean tab, you can see that now the breakdown of those tasks are there. And if I right click, I can copy the data that generated this bar chart or an image of the bar chart. I can copy that and paste it into applications like Word and Excel. The other thing I can do is I can do an animation. So I'm in AutoCAD, and what the software is going to do is move that little block around. In this case, I'm just moving this little circle. processing of the tasks as we go through and creating a trace file, okay? Once again, if I go to the operators, once I get PP person, default circle, I can actually check a person block, update that. And now when I go to animation, you can see that my actual person is walking around in the drawing. And that's actually a 3D person. This isn't a 3D drawing, but if it was, we would see that. Okay, so you can kind of get an idea on how that's working. So we've got the lean chart, we've got some animation, we've got our cycle time calculations. The processing times could be specified in predetermined languages, so we would have the parsing of our cycle times. We also have a report. I'm going to go ahead and get an image of the current display and generate a report. And you can see there's a report showing the type of process where I specified it, the step in the Excel file that I'm using, the location where the work's being processed at. I could have entered a description of the work being performed. I didn't do that in this particular case. The distances that were extracted from the drawing, the processing time, the walking time, and the total cycle time, as well as a picture of the layout. So this is a nice report that just gives you kind of a station summary report for your lean analysis. Of course, you know, as I mentioned, I can change the layout any way I want. Obviously, I could have put L2 anywhere. I could have gone into Autocad and I could say, you know, what happens if the saw was located over here, right? No problem. You go back, you recalculate, your diagram's updated, your cycle time's updated, your reports are updated, and your animation is updated. Easy peasy. Okay, so that's one operator. What happens if we have multiple operators? Well, no problem. I've got a simple little example here. In fact, if I go to, I'll show you an example in the images here. What if I go to a dual operator? We have worker 1 and worker 2. They have 2 different cycles. I've allocated the work accordingly. So in that case, that's what I've done here. I did this task, operator 1, operator 1, operator 1. There's operator 2, operator 2, operator 2, operator 2, operator 1, operator 1. Now, the key thing is that the operators right now, there's no synchronization. There's no type S event here. What that means is that operator 1 is going to do his work in parallel with operator 2 doing her work, okay? So the 2 operators are just working in parallel. There's no blocking. It doesn't really matter the order now between operator 1 and operator 2. As long as the operator 1 tasks are done in sequence and the operator 2 tasks are specified in the spreadsheet in sequence, everything is good. The only time it matters where one comes above another is when we have interdependency or synchronization events, right? Well, we don't have one here. It's just a simple analysis. Let's draw this. So I've got my spreadsheet. I loaded it. I hit calc. All the same locations are specified. There's my work. Of course, I'm in AutoCAD. I can say, you know what, that's kind of silly. Let's bring this all over here and let's rerun that calculation again. Now, in this particular case, there's no internal delay. There's no external delay. Once again, I didn't specify my value added, so it's all non-value added or walking at this point. And you can see my cycle time specified, 81 seconds for one, 81 seconds for another. They're all pretty close. I could choose to say, you know, one of these people is going to have to work longer than the other person. Notice what happens if this task was 30 seconds instead of 20 seconds. You can see now, while the walking didn't change, we certainly have a situation where one operator is getting done before another. Now, we could say that each operator is its own cycle independent, but we all know better. If this is a repeated cycle, operator 1 is going to be waiting for operator 2 to finish before they can repeat their cycles. So I'm going to pick longest here, and now you can see I have a delay. Okay, and I could specify a takt time. I could say, you know what, the actual takt time of this process is 100. And in this particular case, they're now both waiting. Okay, so, and I can animate this and show, animate that and show the operators moving. Now I did specify a symbol for the second operator. Just get it easy to do. And you can see the operators are performing their work. Okay, what about interdependence? Well, let's take a look at it. Now it matters. Let's say that we get down to a point where operator 1 does this task, this task, this task, while operator 2 is doing this task, and this task, okay? 3 tasks for operator 2, 3 tasks for operator 1. Now, for operator 2 to do their 4th task, for operator 1 to do their 4th task, these 2 have to be done. They can't start these tasks, even though they aren't the same time, that's okay. They can't start either of these 2 tasks. Operator 2's 20-second task at VM2 and operator 1's 15-second task at G. These cannot be started until they are both available. So ahead of operator 2, I'm going to insert a row. Okay, I'm going to make that a synchronization event. I'm going to specify that the second operator is operator 1. And I'm going to update. Okay, now operator 1 does these 3 things, operator 2 does those 3 things, they both have to be available. Then operator 2 does this while operator 1 does that, and then operator 1 goes and does this other task, and they're all good. Let's calculate that. I didn't change the layout, so the drawing's not going to update, but you can see the cycle times have updated considerably, okay? In fact, now I'm beyond my cycle time, okay? So now we're in creating this interdependency event. Let's go ahead and animate that. We can see. So what are we going to be looking for? Well, obviously, the only task operator 1 does after the synchronization event is here at G, and the only task operator 2 does after the synchronization event is VM2. So neither operator should go down to G or VM2 until they are both available, which means one of these operators, as we can see here with the internal delay, likely operator 1 is going to be waiting on the other operator prior to that synchronization event. Well, let's watch it. So this operator is going to go to VM11 and wait until they're both available. Neither one of them is leaving this location. Once they are both available, now they can take off and go to their next location and do their work, whatever that work happens to be. So you can see how synchronizations are, events are handled. Okay, the last thing I want to show you, I'm going to leave the analysis here entirely. I'm going to show you a very brief example of a multi-operator event in moving part study. These are quite a bit more sophisticated. I could do a 1 or 2 hour webinar just on multi-operator moving part studies. But I wanted to give you a quick view of what these types of studies do look like. So let's go ahead and load the tutorial example that's included with the software. I'm going to pan over here a little bit. I'm just typing commands in so you can see what I'm doing. I'm going to zoom, window. You can see I've got a little car and a person in there. And I'm going to zoom into this area here. So I have a workplace, right, left, operator. Workplace, I've got a line I drew, it's called my part line. That's one of the things that you'll specify as the vehicle line. It does need to be a straight line. And the and that's pretty much it. So I'll go into Workplace Planner. I'm going to open moving study, which I have right here. And what we're going to see is something a little bit different now in our specification, our tasks. First of all, one thing you'll notice is that I do have my operators. In this case, I have a processing time. I use P, that's fine. And you have your W for your walk time. So M or P can be your manual processing time, machine dependent processing time or manual processing time. It doesn't matter. It's just a user preference. Depends on your reporting. Some people want to determine in their process sheet whether this was a machine dependent processing time or a worker dependent manual processing time. The operator, OR1, OL1, station 1, operator right, operator left. We have our processing time specified. You can see here, the rest of these are walk times. Now, this is a pretty standard task. You can see I'm walking to rack 1, and rack 1 has a fixed location, and I gave it the name rack L1. Now, also, remember that the names of the operators and the names of the locations that the operators perform work at must be letters and or numbers and or dashes and underscores. No other characters are allowed. You cannot put spaces in there. You cannot put periods in there. You can't use exclamation marks. You can't use slashes. So be very careful when you're specifying your operator names and your location names. I would also recommend that you keep them simple. Now, what about this one? This is a little weird. What does at 1C mean? What does at 7L mean? Okay, well, if we go to some of our context-sensitive help, we have a little tutorial on this. That's probably a good way to get a look at that. I'm going to do a moving part analysis. And as I go down here, you'll see this little grid. There are actually 2 grid patterns the software supports. This one grid pattern, the number starts here at the beginning, 1 of the vehicle, and goes to N, whatever N needs to be. It's a user-defined value in the settings tab. Could be 7, could be 10, could be 15, whatever. 1 to 100, 1 to 99, actually. The next character in this location specification is left, center, or right. So am I left of the vehicle as I was sitting in the vehicle, or am I right of the vehicle? So at 1 left would be the front left corner. At 1 right would be the front right corner. At 7 left would be the left rear corner. At should be a 7R, apologize, should be the back right corner. So the point is that this language is allowing me to specify where in the vehicle I'm at. Remember, the at indicates that this is a relative location because the vehicle is moving. This is not a fixed spot. At 1L will be at many different locations as the drawing moves on. Now, in this particular specification, you can even use decimals if you want. I can specify a distance down, and well, I'm not going to detail on that, but if you want to be more accurate, the answer is there are ways to do that. So in this case, obviously I'm at the front center, maybe putting the logo on the front grille. 7 left, I'm in the left-hand side, back, maybe putting in the rear light, and so on as the work is performed. Once again, the sequence of tasks needs to be specified. If there's no interdependency between operator on the right and operator on the left, they're just doing their work. You could do all of the left operator first and all the right operator second, which you can see was done here. It would only be if I have a synchronization event where I'm specifically requiring, let's say, a dashboard installation or a headliner installation, where operator 1 and 2, right, left, have to both be available at the same time. Would I list all the tasks before that headliner event of left and right, then have my synchronization event, then list all the tasks that are being done after that event. Okay, let's do a quick calculation. And you can see here's the operator paths. I'm going to go ahead and make that full screen so it's a little easier to see. And let's go to our paths. We could even put arrows on that. 6 and 6 should look pretty good. Let's see here. Let's do maybe. Yeah, the arrows are showing up a little bit better there. Operators, I have both my operators specified. I do the person block. I do have a starting location for the 2 operators. I do have their speeds. I got 2 different colors for the operators. One's red and one's yellow. Start locations right and left. I can delay them. I could make the operator wait before they start work. I can even allow the operator to work in the prior station so many feet. In other words, once the vehicle shows up before this station, they could cheat and walk into the prior station a certain amount of distance to get started. I also can allow the person to work a certain amount of distance in the following station. they're allowing me to increase the actual cycle time for this operator. Some companies want that to happen. And once again, I can add a delay. So there's a bunch of options here. When we deal with the part, we have a car operates at a certain speed and it's a certain size. And that's just an overall rectangle. It's going to be placed around the car as it moves. We also have an Autocad block that I've specified, so you can pick any block you want for your car. Once again, this is a 3D block. Those are 3D people. If I moved into a 3D view, we could see this working in 3D as well. We'll probably do that here towards the end on the animation. Although AutoCAD, at least my machine in 3D in the editing environment, isn't the best place to do that work. Okay, so we have our routings, we have our people and our paths for our product. So we're going to do a moving part study. It actually saw the ats in here and it figured out we were probably doing a moving part study. It did the calculation. The diagram was updated. One thing that you'll notice how these operators are working here. Everything seems to be fine. What if I slowed down the vehicle? If I slowed down the vehicle, you would think the operators would be forced more closer. In other words, they wouldn't go this far into the station, right? So let's see what happens when I do that. So I'm going to go to the part, which is the car, and I'm going to slow it down. It's not going to go 40 feet per minute. It's going to do 30. Okay. So now when I go into my routings and I recalculate, let me move over here so you can see them. These lines will get shorter. See that? Because the operator cycle time, they now have more time to do other things. The vehicle is taking a longer cycle time in the station. Likewise, if I went in and I changed that and I moved the line rate up to 50, one of these operators can't complete their work in time. Look what happened. So that's not going to work out so well, is it? So let's go back to changing the vehicle speed down to 40. Routings tab and calculate. Okay. And what you're also noticing, once again, I can go into AutoCAD, which is just go to AutoCAD. Once I'm in AutoCAD, I could say, well, gosh, what if I were to start, move the start location maybe, over here, which isn't going to make a big deal. It's only happened once. What if rack L1, that doesn't look like it's in a very good spot. What if rack L1 was actually placed over here? What else doesn't look good? That's probably the worst one, isn't it? This one looks pretty good. That's a nice triangle. These are nice triangles. I don't see anything wrong there. How about over here? What do we have? Looks like rack R1 as well would be better put maybe a little bit closer over to here. What does that do? Okay, so I've moved those locations. What I can do now is I can take a look at my cycle time. So 121 feet, 124 feet. Okay, keep that in mind. Just over 80 seconds maximum cycle time. Recalculate. A little cleaner line, isn't it? 111 feet, 108 feet. We've saved ourselves about 3 seconds of our cycle time. And our drawing is updated accordingly. And lastly, of course, I still have my lean charts per operator. I still have my reports. For each of the operator cycles, my drawing, and my animation. Looks like rack right one, not such a good spot. It is okay on that one, but it could still be better in a different area. Okay, hopefully this has been a helpful introduction to Workplace Planner, both static and moving studies. As always, if you have questions, feel free to contact us. We're always glad to help. There's a question here, is it possible to export the routing file directly from Assembly Planner? So in the case of a moving part study, the answer is actually yes. The file that we're looking at here in line balancing, this file here, okay, which is the list of tasks that each of the operators are performing in a moving part study. If you think about it, how would you know what tasks the right operator does and the left operator does in this station? Well, it's because you did an assembly line balancing study. Now, the problem with the assembly line balancing study is it may have estimates for walking, but it won't know the actual walking because in line balancing, you're moving the task to the station. So this is really a post-line balancing validation of cycle time, taking into account walking. So yes, in the line balancing module in Assembly Planner, I can export to Workplace Planner the list of tasks and task times and task descriptions for each operator in this station. And then I do my calculation, the software updates the walk times, generates the diagram, and gives me a much better view of my cycle time. I may find in my Workplace Planner study, if I was really close to the cycle time, that there's just no way to perform this work, in the cycle time that we thought it would take when we were doing line balancing because the walking is so substantial. In that particular case, obviously the first goal would be to fix the layout so the walking isn't substantial. But if that can't be done, I would have to go back into Workplace to Assembly Planner, modify my line balancing study, republish it, and revalidate my results. One nice thing about the fact that Workplace Planner can parse the codes, MTM, MODAPS, most, is the fact that if I've got my predetermined time study in Assembly Planner and I did my line balancing in Assembly Planner, when line balancing exports the tasks to Workplace Planner, it will also export the predetermined time codes, allowing Workplace Planner to parse those predetermined time codes and then add the predetermined time codes for the walk tasks. So you do end up at the end of Workplace Planner with a very accurate, layout-based, visual and quantitative, predetermined time study validation of your cycle time. All right, everyone. Thanks for your time. If you have any questions, as always, please contact us here at Proplanner. Thank you.